has gone out via the AAS press list. And although I don't have yesterday's press conference videos online yet in the webcast archive, they will be online by lunchtime today, lunchtime Pacific. All right, so yesterday we had two briefings that both touched on exoplanets. Today, another briefing that's mostly about planets and exoplanets and how they form and the stars that they form around. The reason for that is because this meeting had more exoplanet papers than any meeting we've had before. And in fact, I think we ended up having to schedule 3 parallel exoplanet oral sessions at the same time in order to squeeze them all in. Which is kind of frustrating for the exoplanet folks because they might want to be in more than one place at a time. So today we're going to talk about formation and some of the mysteries of how planets form around stars. You can get insight into that by looking at the stars themselves or at the planets themselves. So we're going to have 4 presentations that touch on both of those aspects. As usual, I will introduce the 4 panelists, and then they'll speak in order, and then so you'll hold your questions, and then we'll have the Q&A at the end. All right, so today's presentations are going to go from here to there. We're going to start with Carol Grady from Eureka Scientific talking about the eroding disk of the young M-star AU Microscopium. Then she'll be followed by Elizabeth Bailey at Caltech talking about the hot Jupiter period mass distribution as a signature of in situ formation. Then Aparna Bhattacharya from NASA Goddard will speak on exoplanet masses, challenging the core accretion theory of planet formation. And then finally, David Bennett, also of NASA Goddard, Microlensing challenges the core accretion runaway growth scenario for gas giants. So Aparna and David are colleagues, and their presentations are somewhat coordinated. All right, so with that, I'm going to turn it over to Carol. Now, Carol's asked to do her presentation sitting down, so I'm going to swap our HDMI cable. And with any luck, everything will work.
Hello. Those of you who are over in the extreme end of the session, I'm sorry about the occultation. But now, this is the result of a continuing program that we have had using both Hubble and the VLT's sphere instrument. I'm going to be talking about the Hubble portion of it. And the first thing is, AUMIC is a red dwarf. It's fairly nearby at under 32 light years. It's actually unusual in that we know its age very well. It is a member of the Beta Pictoris moving group, and as a result, people can construct an HR diagram and use guilt by association to figure out the age of the system. So it's about 24 million years old. It is a star which has an activity cycle. 5 years has been claimed for it. It's very active. And it has a circumstellar disk. The disk is viewed edge-on, which means you can see features which extend above the disk. And it also has a planet. This is work by Peter Plavchan that he reported first a couple years ago, and then has confirmed with TESS data. So it's got presumably a Jovian mass planet in a 1-month period. Now, what we've done is use coronagraphic imaging. So we basically put a fist over the star, and it's exactly like walking down the beach at sunset when you're trying to see, is that your friend who's got the ice creams you wanted? And so you just stick your hand out and block the light and improve your contrast. So we've been using the Space Telescope imaging spectrograph. The first three of these are from 2010, 2011, 2017, and 2018, this last summer. We used a different coronagraphic aperture for the last observation, so the field of view changes. Now, what if you have, okay, I have no idea how to do that. Okay, if you notice, there are these little lumps in the arm on the left, which don't stay in the same place. In fact, they are moving outward systematically. And you can see this motion on time scales as short as 8 to 9 months. So we've been tracking these for a number of years. This was called to our attention by our SPHERE colleagues. They used AUMIC as a commissioning target, and they saw all the same features, but found that they weren't at the same place. So this was something of a surprise for them. What we've done more recently is we've combined ALMA data, which has provided a mass estimate for the disk, including larger bodies than just sub-millimeter sized grains, using the scale height of the disk to get that. The mass estimate per feature, and the number of features with proper motions, in other words, motions on the plane of the sky, indicating that they are escaping. And this appears to be about 3 per decade, but that could be uncertain by 1 to 2 more. And what we find is the remaining disk lifetime is estimated to be about 1.4 million years. And when I did this last summer, my initial reaction was, so I hadn't expected that. And the reason I hadn't expected that was we've been imaging disks around other stars. We've got a couple G stars at 2.3 gig a year. And then there's always our system, which has debris belts, which are still going strong. We had lovely photos over last week of Ultima Thule, which is one of the planetesimals in our Kuiper belt, provided by New Horizons. Now, the other thing that I should estimate, this is still a work in progress. We do not know the mechanism responsible for ejecting these things. Thus far, we have a large number of mechanisms which have died very variously messy deaths. We're hoping that being able to track features like this one and look at how its aspect ratio changes over time may give us some insight. The size of these things is commensurate with the size of coronal mass ejections in our outer system. So these are big structures. And we have a couple other early M stars where we think we're looking at the same phenomenon, which have the distinctive feature that the outer portions of their disks look like Swiss cheese. So the disk lifetime estimate that we have that shows going to be basically over, certainly by 30 million years, is consistent with estimates for a deficit in M-star debris disks after about 30 million years. It's totally different from what we've seen around A stars, where we've been able to image disks out to essentially the terminal age main sequence of the star, or G stars, where, again, we can do it indefinitely, and we live in a two-belt system. What this suggests is that processes which depend on disk survival may be inhibited in systems around young M stars. And this includes the delivery of water and organics to terrestrial mass planets in the habitable zone. So we would predict that, in fact, we're not going to see much evidence for water or organics, except in the population of systems which started out more massive and have slimmed down in the radiation environment of the star. So there's been a lot of interest in looking at M-star planets. They're easy to find. There's a bunch of them which are nearby, etc. They may not be like the young Earth. They may not be even like the old Earth. So, so just a caveat, we may have found the limit to habitable planets. So, we are also pursuing this system in terms of a multi-wavelength study of the star. There's a poster on that by Kowalski et al. Tomorrow. And this is just a work in progress, and we hope to be able to keep this going. Hence, to future TAC members, we need telescope time to take it from here. Astronomers tend to like projects with beginnings and ends. And the problem is what we're finding is phenomena which take longer. So.
All right, thank you very much. You can come up, Elizabeth.
Hi, my name is Elizabeth Bailey, and I am a PhD candidate at Caltech. And I'm going to be discussing some new evidence that we found that suggests that hot Jupiters actually form close to their stars. So when hot Jupiters were first discovered in the 90s, it was a huge surprise to astronomers because up until that point, the only example that anybody really had to work off of to understand planet formation was our own solar system. And in the solar system, I mean, there's really nothing orbiting interior to Mercury, not even a belt of asteroids. So for there to be giant planets, not only well within the snow lines of their stars, but also well within the orbital distance of Mercury, presented a major challenge to the existing understanding of planet formation. And so in response to this discovery, there were a lot of scenarios put forth as potential ways that hot Jupiters could actually start out by forming like that several AU distances from their stars, similar to our own giant planets, and then migrate all the way in. And this is still the dominant paradigm for what people think is the way that hot Jupiters form. But in recent years, there has been a sort of another possibility which has been gaining some traction in the literature, which is that of in situ formation, where the hot Jupiter actually just forms close in. And so that is what we address in this work. So here's a plot showing observed exoplanets, the semi-major axis in mass in log-log space. And you can see those two clumps in the upper part of the graph are the hot Jupiters and the cold Jupiters. And I've shown our Jupiter on the plot too as the yellow mark. Our Jupiter is actually a so-called cold Jupiter in the framework of exoplanets. And you'll notice on this plot that there is a region that isn't really populated with any planets, and that's called the desert in the literature. And the question is, what sets the boundary of the hot Jupiters with this desert? You'll notice that this inner boundary of the hot Jupiters is actually pretty sharp looking. And generally, when it comes to planets or asteroids, when things scatter from their original formation location, it tends to create a scattered appearance of their distribution. So that seemed like a clue that this sharp inner boundary of the hot Jupiter distribution might actually be a signature of their formation close to their stars. So taking this and seeing if we can test this hypothesis, we devised a rough, simple model for how we might expect hot Jupiter formation to play out in the inner regions of protoplanetary disks. So what we took into account in our model is that the disk, protoplanetary disks are accreting onto their stars, and we assume that that accretion is supplying the hot Jupiter with material. And additionally, we make the point that there is an innermost radius of the disk where we would expect planet formation to be an active process, because stars tend to carve out holes in the middle of their disks. And we take the radius of that magnetospheric cavity to be the innermost place where we would expect the hot Jupiter to form. So taking these assumptions into account, we predicted a expression for the inner boundary of the hot Jupiter population, which actually agrees quite well with the observations, as you can see in this plot. So overall, if our interpretation is correct, what this appears to suggest is that hot Jupiters actually in most cases form close to their stars rather than forming far away like Jupiter and Saturn. And if that is correct, then it would mean that hot Jupiters are distinct in their origins from Jupiter and Saturn and other so-called cold Jupiters. And our work is published in AppJ Letters if you want to check that out. Thanks.
Hello, I'm a postdoc at NASA Goddard Space Flight Center and University of Maryland College Park, and I'm going to talk about the cool exoplanets discovered by microlensing, and also this talk is going to continue to the next talk. So first, I would like to introduce what exactly is microlensing. So for that, let's say this is our source that's in the galactic center, and I'm going to shine at Mariella. So she's our Keck telescope, and this is our this ball here is our lens system that is in the galactic disk. So it has some strange star spots, but just ignore it. It's fine. So this is in our galactic disk. So as this star is moving and coming in front of the source star, the light from the source star gets gravitationally bent by the mass and the gravity of this star. And as a result, what we see is a very magnified brightness of the source star. Also, if it happens that this star, if this star happens to host a planet, then as this planet comes in front of the source star, then the light from the source star gets bent by the gravitation field of the planet. And as a result, as you see, we can see a planetary anomaly over there. And hence, so this whole system, this lens actually works like a nature's own magnifying glass. And as you see, this is how it really looks in the real data. Now, this is one particular event that I would focus on today in my talk, is this Ogle 2012 Bulge 950, where this event was in 2012 it happened, and as you see in the boxes that are in the bottom, that these dips show the detection of the planet. But even though this happened in 2012, we decided to follow up this event with high-resolution two telescopes, Hubble Space Telescope and Keck Laser Guide Star Adaptive Optics, on May 23rd, 2018, simultaneously. And why we decided to do that was because during the event that, as I showed, when this is the situation, the light from the source is actually very magnified, and we are not able to see this lens system actually. So we cannot actually see the host star and the planet, but in spite of that, we can still detect the planet. So during the event, as you see, the lens is very faint. And as few months later and even few years later, 5 to 6 years later, this whole thing has moved away. And then the source brightness has come back to normal. And what we see is basically elongated source and lens. So we don't see them resolved, but we still see them elongated. And if we observe a decade later, then we will see them totally separated. So this is the time when 5 to 6 years later, that's when we took the observation. And what we saw from Keck image is that the lens and the source, they are elongated. And we were able to detect the lens and source, and we were able to measure the separation between them, which was 34 milliarcsecond. Now, how small is this 34 milliarcsecond? It's literally like locating a dime from 110 kilometers or 68 miles away. So so I'm over here holding this dime, and you're on top of Mount Rainier, and you're able to locate this dime from Mount Rainier to here. So that's how small it is, and that is a really difficult thing to do. So for that, we really had to understand the Keck images very well. So once we have got that, we can actually get the mass measurement of the exoplanet. And what we got is it's a 39 Earth mass planet. So we have no planet like this kind of planet in our solar system, because Neptune is like 17 Earth mass, and then Saturn is like 95 Earth mass. And this is a really cold planet that is between Saturn and Neptune. And this is very important because the leading planet formation theory, core accretion, actually predicts that these kind of planets should be rare. But the question is this kind of planet really uncommon, really rare? Or is it like the theory is built so that like it can kind of support the solar system model? And maybe our solar system is sort of biased maybe, or unique. So because of that, it's a really interesting observation, and Dave is going to follow more on this. But just to end my presentation, that WFIRST, which will fly in mid-2020s, will use this method to measure mass of hundreds of such exoplanets and reveal many exciting signs. My poster is at 24709. Please check it out. And if you have any questions, you have my contact. Yeah, just contact me. So that's it.
Your dime.
Switch the slides.
Okay.
Okay. Hi, my name is David Bennett. As Aparna mentioned, I'm located at the NASA Goddard Space Flight Center, and I also work for the University of Maryland. I'm presenting results based on a paper that's actually presented by a colleague, Daisuke Suzuki. He's in the back row. You can raise your hand, Daisuke. His presentation is going to be in the WFIRST special session on recent results from microlensing as a pathfinder for WFIRST. Okay, so first I wanted to say a few words about planet formation theory. Planet formation theory is pretty important even if you're only interested in habitable planets, because it's not just enough to have a planet in the habitable zone. You have to have chemicals that are are consistent with life and a history that's consistent with the development of life. And so the better we can understand planet formation, the better we are able to predict which planets might be habitable. Okay, I started my career as a cosmologist, and I must say that planet formation theory is very, very much harder than cosmology theory. In cosmology, theorists can do, a straightforward prediction, and observers can go out and check it and determine whether it's true or false. And planet formation theory is much more difficult, and such clean tests are not so easy. Okay, the leading theory of planet formation is the core accretion theory, and it's originally based on the solar system. And one of the key aspects of the core accretion theory is this concept of the snow line. And this plot shows a diagram of a protoplanetary disk, and the temperature of that disk changes very close to the star. There's a lot of stellar heating, and so the gas and material in the disk is very hot, and it's too hot to form ice. Water would be in vapor form. But as you move out, and in our solar system at 2.7 AU, we expect that the disk was cool enough so that ice would condense. And this means that there's more solid material available for planets to form. And the implication, according to the core accretion theory, is this is where Jupiter formed, and the giant planets in our solar system are all located now beyond the snow line. Okay, and if we look at the planets that we know have already been discovered, this plot shows them as a function of their mass and their separation, but their separation is given in units of this snow line. And so you see the vast majority of planets are found by the transit method, primarily by Kepler, and now we're getting many more by TESS. There's also many short-period planets found by radial velocity, and some long-period planets as well. But it's only microlensing that can really study the longer-period planets beyond the snow line at a range of masses, going from super-Jupiters down to sub-Neptunes, and if there were Earths there, we should be able to see them as well. Okay, so at present, the sort of state-of-the-art statistical study of planet properties from microlensing is this MOA-2 survey result, also led by Dr. Suzuki. And here I show a plot of the planets that are the 30 planets from this study plotted as a function of their mass ratio. That's the black histogram at the bottom. And you see that as far as planet discoveries go, the distribution is pretty flat in mass ratio. However, the planets, super Jupiter planets, are much easier to detect than Neptunes or sub-Neptunes. And so to get the real occurrence rate, we have to correct for this detection efficiency. And we do that, then we see the red curve, and that indicates that the Neptunes and sub-Neptunes are much more common, and probably the most common types of planets out beyond the snow line. Okay, now to compare this to theory, it's a little complicated. We compare to a type of theory referred to as population synthesis models. Okay, but the planet formation process is so complicated that these population synthesis models have to use approximations for multiple different very complicated physical processes that can sometimes be calculated in detail, but to simulate a large population of planets to compare with observations requires this type of simulation. And as Elizabeth alluded to earlier in her presentation, a key question in this planet formation is planetary migration. And it's not really understood very well. It was once thought that it would be very important. Now some people are arguing that it's not so important. And so the two groups that have done population synthesis calculations with us have done calculations with their standard migration and also turning migration off. And as you can see at the giant planet side, it looks like turning migration off or down very much probably helps to fit the number of giant planets that we see. But it doesn't help at all with these intermediate mass planets. And so in all cases, the two different population synthesis codes and with and without migration are failing to produce these this number of sub-Saturn mass planets. And so this kind of answers the question that Aparna asked, that these, it's not an accident that this Ogle 2012 950 event was, found to have a 40 or 39 Earth mass planet. Actually, those are fairly common. They're more common than Saturn's or Jupiter's. And so the lack of such planets in our own solar system is more likely to be due to random chance or an accident, and it's not actually a sign of the theory. And so, the fact that the core accretion theory predicts something that looks like the solar system is just more likely a coincidence than actual success. Okay, and to explain why it is that the core accretion theory has been predicting this gap, I wanted to talk a little bit about this runaway accretion process. And so this diagram on the right shows the traditional core accretion model for giant planet formation. Initially, you get roughly 10 Earth mass core that begins to slowly accrete hydrogen and helium gas. And then once the amount of gas equals the core size, then the accretion goes through this runaway accretion process, and you accumulate mass very quickly. Okay, so you want to think about how this might finish. So one possibility is that that radiation from the star or from a nearby star might drive the gas out of the system during that few million years of the slow accretion. And if that happens, what you end up with is something like a Neptune. And we see those are quite common, so maybe that happens a lot. But then, according to this, the other likely thing is that the gas would leave the system after something like a Jupiter has formed. Okay, but the odds that it would stop just in the middle of this very rapid accretion process would seem to be very low, and that's the basic reason for this gap or desert in the distribution of cold planets that was predicted by early versions of core accretion. Now. So people are doing more sophisticated calculations, and in particular, the original calculations were just spherically symmetric collapse in basically one dimension. And so now they're doing complicated hydrodynamic simulations in 3 dimensions, and this video shows the final result of one of these calculations, or a result in image. This is a protoplanetary disk being simulated. They were just rotating it around to show what it looks like. And in that sort of blue region, there's a planet. And when we look at the cutaway, we can see where the planet's forming. And so basically, you see that the accretion is sort of going through this protoplanetary disk, circumplanetary disk, and in fact, we expect that such things have to be there because it explains the formation of the moon systems around Jupiter and Saturn. Okay, so the video that I've used here is from Judith Szilagyi from Zurich, and her simulations actually don't have this runaway accretion process. Now, the difficulty is that it's very computationally expensive to do these calculations, and so this calculation that she showed, it took her 3 months to do, and so it's hard to probe all the different possible parameters. And so not everyone is convinced that this is the solution to this problem, but but it's clear that planet formation theory kind of needs all the help it can get from observations, and so this is the motivation then for the exoplanet survey, exoplanet microlensing survey of the WFIRST mission. I'm showing here a plot from a simulation by Matthew Penny, comparing planets discovered by Kepler to predicted planets discovered by WFIRST, and you can see that we're able, with a combination of these methods, we're able to discover planets down to well below Earth mass at all separations. And in fact, microlensing, it's possible to detect even free-floating planets out at infinite separation. So it really is that we're sampling the planetary distribution at separations from 0 to infinity. Okay, so as I said, the talk on this is going to be given by Daisuke at the special session on WFIRST this afternoon. So thank you.
All right, thank you all very much. So we're going to start by taking questions here in the room. Christine Pulliam from Space Telescope Science Institute has the roving mic. If you have a question, raise your hand, wait for the mic, and when you get it, please identify yourself and your affiliation. So we'll start down here with Clara. And then again, if you're on the webcast, please queue up your questions via the text chat, and Carrie will relate them to us.
Hi, I'll start with a question for Dr. Grady. What is it about M stars that we think might make them unique in having these disappearing disks?
Well, M stars are extremely active. They have periods of quiescence, but in our week of XMM observations, we got a lot of flares. Big flares, little flares, yes. So they are not nearly as quiet, and they keep this up for at least the first giga year. And the other thing is, if you're going to go by habitable zone calculations, your habitable zone is almost down at the co-rotation radius, about 0.08 AU. So you're parking your planets that you think might be suitable places to be in the temperature range to support liquid water in probably the least benign radiation environment. So it's a combination of effects that basically can strip atmospheres from planets and make life much more challenging for life.
Thank you. I think I forgot to say Clara Moskowitz with Scientific American. Can I add one more question for Elizabeth Bailey? Can you kind of clarify what makes it so surprising that the hot Jupiters would form in situ rather than further out? I think it has to do with the snow line, but if you could talk more about that.
I'd say the most surprising aspect of that is for so many years, the only example we had was our solar system. And at the distances where hot Jupiters are found from their stars, in our own solar system, there's like literally nothing there. So it's a big difference between nothing and giant planet. And that was a surprise.
Okay, thanks.
Okay, we'll take Alan first and then come back over to this side of the room.
Hi, I'm Alan Boyle with GeekWire. I wanted to follow up on what Clara was asking for Dr. Grady. I think that you said that the mechanism maybe isn't known and that some of your hypotheses died messy deaths, but it sounds as if that idea of active stars is kind of the suspect that you're focusing in on.
Well, it's where we've got our current set of hopes. But it's when you're starting to talk about phenomena on orbital timescales of giant planets, you're typically talking long-duration phenomena. And it has been very difficult to persuade observatories to cough up the observing time. to be commensurate with that. So it's still a work in progress.
Okay, I think, Ethan, you had a question?
All right, so I actually have two questions,
You
but the
identify
first
yourself.
one is either for Aparna or David, and I don't care which of you takes it. And that is, you talked about that we have these models of like the runaway gas accretion model, the core accretion model of the solar system. And if we make these sort of naive assumptions about how it works, that you would expect sort of this bimodal distribution, and we actually don't see a bimodal distribution. We see actually there's plenty in between Neptune mass and Saturn mass. Is there a takeaway that's anything more substantial than this naive model is too naive?
Well, I wouldn't say it's exactly a naive model. It's, I mean, the core accretion theory actually has sort of multiple complicated physical processes that aren't completely understood, and they're believed because we see planets. And so, this is one process that was considered to be part of the core accretion theory, and so we think it's it's unlikely to work the way that it was originally thought. But most of the practitioners in planet formation theory think that it's basically that this is something that needs to be fixed in core accretion theory. There's another issue that they've been debating is the amount of migration there is, right? And it had been thought that migration was really needed to explain these hot Jupiters, but as we saw from Elizabeth, that's no longer so much the case, and so basically, with microlensing, we're sort of taking the first look at the formation of planets, or the distribution of planets in orbits like the ones in our own solar system, and so we see that the core accretion model in this runaway gas accretion process is not really adequately describing them. So the thing is, the theory is so hard, it's not like there's an alternate theory that kind of explains the same thing. There is an alternate theory called gravitational instability, and there's a reasonable chance that it plays some role in planet formation, but it seems unlikely that it's going to supplant the core accretion theory. There may be some mixture.
I mean,
of the two.
doesn't Saturn not have a sufficiently large core to even cause this scenario, as far as we know?
I think Saturn actually is thought to have a pretty large core. There's some more debate, I think, about the mass of the core in Jupiter, but a lot of this involves, sort of understanding equations of state at very high pressures that are very hard to produce on Earth.
Can I ask a second question?
Only if you identify yourself.
Sorry. I'm Ethan Siegel. I write Starts With a Bang, currently hosted on Forbes. And my second question is for Elizabeth. You talk about how planets actually form. And as I understand it, based on our solar system, the leading theory is that actually we probably did form a large world in the inner portion of our solar system early on, and it was swallowed by the sun. And that's why we only have these tiny things inside, even though we're orbiting a relatively large star. And so I had understood that was the leading theory that was a part of like the Grand Track model and things like that. Why is it such a surprise that we would form large planets in situ also?
So I think the theory you're talking about isn't referring to like a single like giant planet falling into the star, but more like super Earths maybe.
That's fair.
Yeah. So what was your question again?
So why is it a surprise that you would form large planets around there if they stick around and don't get swallowed?
If they stick around and don't get swallowed?
Yeah.
Well, it's not really a surprise to me, but it's a surprise to the field.
Well, I'm wondering, is my mic live, Joe? Okay. So, I mean, there's got to be some kind of tension between the heating close in and the accretion coming from the disk.
Yes, exactly.
I mean, how's this? Because I think when the hot Jupiters were first discovered, it was like, well, they obviously can't have formed there because it's too hot. The gas would boil off.
Right.
So what is enabling the gas to stay there? I mean, how can we have a Jupiter as opposed to just a big old, giant rock?
So one major sort of factor that people thought meant that there could not be hot Jupiters forming in place close in was that it was assumed that there were not suitable cores available. And that was largely due to the lack of stuff orbiting close in our own solar system. I mean, to undergo core accretion, you need to have a core that's like 10 Earth masses-ish. And so we don't have anything like that in our own solar system. And in fact, interior to the approximate snow line, we just have little terrestrial planets that are quite puny and not suitable. Like the Earth would not be big enough to undergo core accretion. So actually, then it became gradually known through observations of exoplanets that super Earths are pretty common close in. And that actually, they're actually so common that only like 1% of them would need to undergo core accretion to runaway accretion to account for the entire hot Jupiter population.
I can actually add something to that. So there was a thing called the minimum mass solar nebula, which people figured out based on, looking at what's the planets in our solar system, what's the minimum mass nebula that could account for that. And a lot of the planet formation theory early on was developed relating to this minimum mass solar nebula. And with that, there's not really enough material to make a core for a giant planet.
Yes, the minimum mass solar nebula is essentially an approximation that people used before they really knew what to do because there weren't really observations to work from. So they essentially said, let's take the mass of all the planets and kind of spread them out and say that that was the initial disk material available for planet formation, and that a forming planet would have kind of an annulus of mass, and that would be what it would have to form from. And because we don't, it has become known through exoplanet observations that our own solar system's architecture is not characteristic of other systems.
Okay, we'll come back over to this side. Steve Marin first. Then we'll go to Martin, then we'll come back over here. Actually, Leslie had one, right? Okay. Carrie, do we have any online?
So, my question for Dr. Bailey was answered just now. For Dr. Grady, if I understood correctly, you've concluded that it's unlikely for planets big enough to, at least from the aspect of size and mass, to be habitable to form around an M dwarf in the habitable zone. I think I understood you to say that.
Well, what we've found is that if you look at the data for AUMIC, it says there probably was time to produce small planets close in, but the process that seems to be missing would be where the disk is coupled to the planet because of being bombarded by sun grazing or star grazing bodies that are delivering the water and organics, because we think the Earth formed dry and then inherited its ocean and its organics, which have made, among other things, this meeting possible, by being basically pelted by asteroidal material, by being pelted by cometary
That was not
material.
my question. It was
So
My
we think,
understanding of what you said
we
would
think
stimulate
that the
that.
small planets form, but if you look at them, and you have to look at them at a range of ages, what you're going to, I think, find is that they don't have a clear presence of water at 150 million years, as in the case of the Earth, and they don't have surviving atmospheres in the older systems.
Okay, that does answer it.
So, Martin?
Martin Ratcliffe, freelance and Skyscan. I think this may be a question for David, but I'm not sure. I didn't know runaway gas accretion was a thing, and I think I missed part of the explanation. But my idea of a gas accretion disk is it's predominantly hydrogen, helium, plus a few little others. So how do you get in essentially a hot disk, unless you're out in the cold disk? What is the mechanism that triggers this runaway accretion by presumably cold gas? Did I miss something there?
Yeah, well, I mean, it is out in out beyond the snow line, and the thought was, I mean, the one-dimensional calculation, hydrodynamical calculation, indicates that once the gas mass gets to be equal to the core mass, that the increasing pressure at the bottom of the gas distribution then builds higher density that then can attract more gas quickly. And it's it's important that the gas has to be able to cool, but so it is it is a somewhat complicated process when you do it, and to do it properly you have to include the angular momentum and realistic radiation transport, which wasn't done initially. But it has been thought that this is, the main reason why there aren't these, I mean, this has been used to predict this mass gap.
Okay.
I think I can.
Sorry, go ahead. Go ahead.
I can maybe just say a little bit simple. Is like, so beyond the snow line, it's ice. It's solid enough that they can just stick together, start forming a core, and once the core gets really big, it starts attracting all the gas together. And once one planet becomes like one core becomes really big and starts attracting all the gas, and all the gas just forms, one big giant planet. So it just becomes either like a small planet, or it just becomes a giant planet like Saturn, Jupiter, like that. So that's how they explain, or the theory is trying to explain that that's why we don't have this 20 to 80, yes, this gap, because how is this intermediate, how is this stopping, this gas accretion is stopping. So it's like that.
Okay, now we'll come down here to Leslie Sage.
I'm Leslie Sage from Nature, and this is for Elizabeth. It's an extension of Rick's question. What specific physics is there in your model that allows the cores to avoid being ablated or tidally sheared apart?
Are you talking about the core that...
core for the hot Jupiter.
Ablated by the star? Or?
By the star.
Well, being tidally sheared apart isn't really an issue for the hot Jupiter at the distances that I'm referring to in the plot that I showed. But I mean, if they get close enough, they will be tidally sheared apart. I'm not entirely sure I understand your question.
Okay, so you have a planet at 10 stellar radii, and the core is going to be subject to severe radiation and tidal shear. How can you actually get a core to form under those conditions?
Well, it is possible that what our scenario is referring to involves migration of the super Earth toward the inner region. We still kind of categorize that as being in situ formation because, the vast majority of the mass would have been accreted in situ. But we remained agnostic as to the origin of the cores in that study. So that is definitely a topic that should get some future work.
Okay, I think we have at least one question online.
All right, this question comes from Megan Bartels at space.com, and this question is for Carol. Could you mention one or two potential explanations you considered and why they didn't work out?
Okay. Well, we considered whether we were looking at the interaction of a planet at several tens of AU with our features. And basically, we have not seen maintained over time a preferred geometry which would suggest that we are tracking a planet at large distances. We also considered, there were so many mechanisms.
Well, you mentioned that they're consistent with the size of coronal mass ejections.
Yeah, that's...
What about coronal mass ejections?
Well, that's what we have to do then is show you have a coronal mass ejection in the right energy range, and then at the appropriate time later, you see something trekking out. This requires not quite coordinated X-ray and other data. And logistically, it is challenging. I mean, we thought when we got a week of XMM time that we died and gone to heaven because then we had a much better chance to get the flare frequency distribution and be able to say how frequent are these things. I mean, techs like to know little things like that before they're going to give you a chunk of observing time. And so some of this is just, it's logistically difficult to organize an effort. And it is, and the other factor that we were fighting was that Chandra and XMM both observed AUMIC about 10 years ago. Chandra saw no flares. 50 kiloseconds, no flares. XMM saw 6. So going from that to this thing is producing coronal mass ejections with the right frequency to be consistent with the stuff that we see heading out that is one of the things that we are hoping to solve from our current program once we have the flare frequency distribution. So some of this stuff just takes a little more time to sort out. And we got all of our XMM and other data in October.
Another question? Okay.
This question comes from both Monica Young at Sky and Telescope and Pamela Gay at Astronomicast. So in terms of these hot Jupiters, again, we've seen evidence of exoplanets evaporating away. So if these hot Jupiters form in situ, what's to stop them from evaporating away before we can see them? Or is it possible that we're only seeing super young stellar systems?
Okay, thanks. So for the case of, I don't know if you remember the desert that I showed in that picture, but the boundary of the desert with the sort of super Earth mass planets is thought to be shaped by photoevaporation. However, hot Jupiters are so massive that they only lose like maybe 1% of their mass over their lifetimes due to photoevaporation. Photoevaporation doesn't significantly change the mass of hot Jupiters or ablate them away once they get to that size.
Okay. I've got time for one more. We'll take one more from the back here.
Hi, this is James Lowenthal from Smith College in Massachusetts for Elizabeth Bailey. I know that recent images from ALMA show beautiful, smooth protoplanetary disks, nice and clean. But what role could turbulence and inhomogeneity play in the inner disks that might help hot Jupiters survive?
That might help them survive.
Grow and
grow.
survive.
Well, turbulence is thought to be implicated in the specifics underlying the disk accretion. Disk accretion, viscous accretion rates tend to be about 10 to the minus 8 solar masses per year from observations, although there is a spread in those observations, about an order of magnitude in each direction. So anything that impacts the rate of disk accretion will affect the specifics of this picture.
Okay, that's all we have time for. Thank you all very much. A few quick announcements for the press registrants. Reminder that at 11:45 in this room, we'll have a media availability with representatives from the 30-meter telescope project to talk about what to anticipate as they restart or attempt to restart construction of the telescope on Mauna Kea. There will be a press reception again this evening. This one will be hosted by the Chandra X-ray Center, and we'll have an opportunity to hear from the director of the Chandra mission right now, Belinda Wilkes. And then, so that's at 5:30 in this room. And then if you haven't signed up for the press dinner on Thursday evening, please go to the link in the press kit and do that. And the same applies to the tour of LIGO Hanford on Friday. If you want to attend, please sign up for that. I'd like to have that list complete by tomorrow so I know how big a van I need to rent. We have a press conference this afternoon at 2:15 Pacific. It's about the Energizer Bunny of sky surveys. Oops, whatever. It's the Sloan Digital Sky Survey. How it keeps going, and we're going to hear some of the most recent results from that project. Again, we'll have briefings in the morning and the afternoon, both of the next 2 days as well. So we've got a lot more interesting science to come. Thanks again for coming this afternoon, or this morning, and we look forward to seeing you again this afternoon.